welcome to the State Library. My name is Jessica Schrei, and I'm a reference librarian here. We're thrilled to have you here today for the start of our 2023-2024 Author Talks series. We'd like to take this opportunity to thank the House Broadcast Services and the Bureau of the State House for their help setting up this event today. Today, we're honored to be joined by renowned astrophysicist and author Avi Loeb. Dr. Loeb is a professor of science at Harvard University. He received a PhD in physics at the age of 24 and in 1993 joined Harvard, where he became the longest-serving chair of the astronomy department. In addition to being a New York Times bestselling author, Dr. Loeb has published nearly 1,000 papers on research topics ranging from black holes to extraterrestrial life. In 2012, Time magazine listed Dr. Loeb as one of the 25 most influential people in space. Today, Dr. Loeb will be talking about his new book, Interstellar. Interstellar is Dr. Loeb's counterpart to his 2021 bestseller, Extraterrestrial, which introduced readers to the theory that intelligent life exists beyond Earth and that our solar system has been visited by alien technology. Interstellar delves into this theory further and provides readers with a realistic view of what alien contact will look like. Before Dr. Loeb begins, I want to let you know that his talk is being recorded and will be uploaded to our YouTube channel. He'll speak for 30 to 45 minutes, and then there'll be time for questions and discussion. When we get to the Q&A portion, a staff member will walk around with a microphone for you to use, since this talk is being recorded. Also, if you need an assisted listening device, we've got them right there for you, so just let us know. Without further ado, I'm happy to present Dr. Avi Loeb.
Thank you so much. It's a great pleasure to be here. We are living at an exciting time. First of all, we produce technological kids that may be more intelligent than we are. These are the large language models. We evolved out of chimpanzees by developing a language. Now we are creating AI systems that use language to evolve beyond us. In a way, that's an alien intelligence, but it's our own making. And the question is whether we can look at our technological future by finding packages that arrive to our backyard from far away. And I'm here to describe my attempts as a scientist to find those packages in our backyard and read the postal address on them. And I'll describe an expedition that we just had a few months ago to the Pacific Ocean that ended up successful despite the immense risks that it took, just to illustrate that innovation in science is exciting and may pay off. For all the young people that may watch it, it provides some inspiration to deviate from the beaten path. My book, Interstellar, deals with the implications of finding a gadget that was created by an advanced technological civilization. We could learn from that, and it will bring humanity to a better place by inspiring us to explore space and perhaps to change our priorities from engaging in conflicts throughout the world to actually working together, because we are all in the same boat, the Earth sailing through space. So for details, you might check my book. But first, let me talk about the scientific work that I'm doing that is the basis for the book. So I'm not just preaching, I'm actually practicing what I preach for. And that's a difference that you should pay attention to when you listen to people who popularize science. Many of the most famous names do not practice science. Just check their CV. Many of them didn't write a scientific paper over the past decade. I'm writing papers all the time, doing the science that I preach for. And when people say extraordinary claims require extraordinary evidence, most of them do not seek the evidence. It's a circular argument. If you don't seek the evidence, it will always stay an extraordinary claim. So how do we seek evidence for neighbors in the cosmic perspective? Like finding a tennis ball in our backyard that was thrown by a neighbor among all the rocks that we see very often. So a couple of years ago, I decided to lead the Galileo project at Harvard University, which is engaged in the scientific research on searching for objects that were manufactured by a technological civilization near Earth. And only over the past decade, we could detect the first objects from outside the solar system. And they could come in two flavors. One is space trash, just like our own Voyager, Pioneer, New Horizons. When they exit the solar system, they will not be functional anymore. And we are basically polluting interstellar space with trash. You can think of it as plastics in the ocean. They keep accumulating over time. By 2050, there will be more mass in plastics than in fish. So just be careful eating at a fish restaurant here in Beacon Hill. At that time, you might actually eat plastic. So the Galileo project is following several tracks. One of them is a new observatory that is currently operating at Harvard University, and it has a set of infrared cameras looking at the entire sky 24/7, checking if there are any other objects than birds, drones, balloons, airplanes, familiar objects. Is there anything that came from outside of this Earth? And as you know, there was a hearing in the House of Representatives in July with the word extraterrestrial mentioned routinely. That's quite unusual for politicians to take time away from their day job of worrying about national security, societal problems. And there was a bipartisan interest in this question. So that's one of the topics that unifies everyone. And in addition to infrared cameras, we have an optical camera, we have a passive radar, an audio system. We are trying to listen to the sky. And we're collecting the data into computer memory and then analyzing it with machine learning software. So it's not about eyewitness testimonies of people that happen to be at the right place at the right time. These are anecdotal, and we cannot use it for scientific research. It's about using instruments. And we all know that instruments are more reliable than people. FIFA, in the Women's World Cup this year, used video cameras, right? They didn't go to the players and ask, did the ball cross the post? They just relied on instruments telling them, because people have ulterior motives. And so let me show you a brief video that illustrates, that describes the various instruments we have.
Welcome to an overview of the Galileo project's development site, codenamed Pigeon Run. Our instrumentation suite consists of both wide-field and narrow-field sensors. Wide-field sensors are used for target selection and tracking, while narrow-field sensors gather higher-resolution data on potentially anomalous objects. Our main instrument is DALEC, a hemispherical array of 8 infrared cameras. Next to it is the Alcor, a secondary high-resolution optical all-sky camera. Together, these instruments continuously monitor and track objects in the sky, analyzing them in real time for potential anomalous activity. This is AMOS, our acoustic monitoring omnidirectional system designed to detect and record acoustic signatures across the infrasonic, audible, and ultrasonic bands. AMOS also houses an ADS-B antenna for logging aircraft transponder data, allowing us to quickly separate known from unknown objects. Here we have Skywatch, a multi-static passive radar system designed to detect and track multiple objects simultaneously, measuring object positions and kinematics. NPAC-MAN is an environmental monitoring system for measuring local weather conditions. Sensors include an anemometer, temperature and pressure sensors, a particle counter, and a flux gate magnetometer. Next up is Spectre, a radio spectrum analyzer with a wide band antenna for measuring radio and microwave emissions. Beacon is currently our only narrow-field instrument. Beacon is a high-resolution pan-tilt zoom camera capable of 40 times optical zoom. Our instruments collect a wide range of data, all of which is fed to our computing enclosure housed beneath the DALEC and Alcor instruments. Here, data is processed and analyzed in real time. Objects detected and tracked by the wide-field instruments are localized in 3D space and analyzed for unusual characteristics. Selected targets are then sent to the Beacon PTZ for follow-up observation. Finally, data is recorded to disk and uploaded to the cloud via Starlink. These combined systems comprise the current version of the Observatory class system, with many refinements, additions, and upgrades scheduled for near-term implementation at Pigeon Run.
Okay, so that was a brief summary, and we currently have plans to expand the system, have more components, including satellite data, and trying to triangulate objects so that we can figure out the distance. We're planning to make copies of the first system that is at Harvard, place them in many locations so that we will have good enough statistics of the unidentified anomalous phenomena that the US government talks about. Of course, the US government worries about national security. Anything that says made in China on its surface is boring as far as I'm concerned. I don't care about human-made objects, and I'll be glad to deliver the data straight to Washington, D.C. I care about anything beyond of this Earth. And of course, if we see birds, we'll give the images to zoologists that might be very interested. So we plan to go farther away to other locations and make additional copies of this system depending on funding. Each observatory can be named after the donor and costs about a fraction, $500,000 or so, which is not a lot for an observatory. We are also using satellite data, looking at objects from above, not just from below, based on public data from Planet Lab. They have a series of satellites looking at Earth all the time. And we have plans for the future to expand the system and make it more versatile and so that we can visit places on a short time basis. We published about 8 papers already describing the systems we have. And that's one branch of the Galileo project. Another branch has to do with objects that are not close to Earth. They just pass near Earth. And the first object like that originated from outside the solar system was discovered in October 2017 by a telescope in Hawaii. The US Congress decided a decade earlier to search for objects bigger than a football field, which we can detect based on the reflection of sunlight from their surface. And so this telescope in Hawaii was constructed to survey the sky, and it found an object passing close to Earth. So it flagged it as a near-Earth object. And then the object was moving very fast, faster than the escape speed needed to escape from the pull of gravity of the sun. And so this object was declared as an interstellar object, an object that entered the solar system from outside based on its speed. And that was a surprise to me because I did a calculation a decade earlier that no such objects should be discovered by this telescope, the survey telescope, Pan-STARRS, because based on what we know about the solar system, there aren't enough rocks of this size so that the telescope will see one of them over a period of a few years. So I was intrigued, but then as time went on, we collected more data on this object, and it looked like it's not a rock of a type that we've seen before. Most likely it had a flat, pancake-like shape based on the reflection of sunlight as it was tumbling, and it was pushed away from the sun by some mysterious force without showing any evaporation. There was no gas or dust around it, the way comets show. And so it was not a comet of a type that we've seen. It was not a rock in terms of its shape and its push away from the sun. So I suggested maybe it's a thin object, just like a sail, which is pushed by reflecting sunlight. And nature doesn't make such objects. So maybe it's a surface layer from a technological object or a broken piece of a technological object. And 3 years later, in September 2020, there was an object, another one, found that was pushed away by reflecting sunlight, no cometary evaporation. And that one was identified by the same people at the telescope in Hawaii. It was recognized to be a rocket booster from a launch in 1966 by NASA. So here you have it, a technological object, because we produced it, showing the same qualities as Oumuamua, this object from 2017, which means a scout in the Hawaiian language. So we were left with uncertainty because there wasn't enough data to declare Oumuamua technological or a rock of a type that we've never seen before. But I was intrigued, and a couple of years later, after a radio interview, I decided to check a catalog that NASA has for meteors. These are objects that collide with Earth. And search together with my student for the fastest moving meteors in that catalog to see if any of them came from outside the solar system. And we found one from nearly a decade ago, January 8th, 2014, that collided with Earth, and the fireball, the explosion of this object, as it burned up in the lower atmosphere of the Earth, was noticed by US government satellites. And that was intriguing because this object was moving very fast. It was just like Oumuamua, above the escape speed from the solar system. And moreover, we calculated that outside the solar system, it was also moving very fast, at 60 kilometers per second, faster than 95% of all stars in the vicinity of the sun. So it was a fast mover relative to nearby stars, but also it survived all the way down to the lower atmosphere of the Earth. And that meant that it had material strength higher than the rocks that we had seen before, 272 of them from the solar system cataloged by NASA. And that raised the possibility that maybe it's a Voyager-like object, that we sent out the spacecraft Voyager and imagine in the distant future it colliding with a planet like the Earth and burning up in the atmosphere, appearing as a meteor of unusual strength and unusual speed. So to check this out, I initiated an expedition to the location of this explosion of the object to find any materials left over from it. It's not a philosophical question whether it's artificial or natural. We can just look for the materials left over from it. So let me show you a few photos from that expedition, which took place on a ship that was very fittingly called Silver Star. And that's, you will hear a song that has these words in it.
Drifting in my silver star, thinking I am where you are. Drifting in my silver star, thinking I am where you are. Drifting in my silver star, thinking I am where you are. Drifting in my silver star, thinking I am where you are.
So the story started almost a decade ago when the US government satellites detected the fireball of this object. And so 5 years later, we noticed that it moved very fast. So it's 4 years before Oumuamua. It was the first interstellar object ever discovered. And we wrote a scientific paper about it, 2019, 4 years ago. And the paper was rejected because my colleagues argued, we don't believe the US government data. And at the time, I was chairing the board on physics and astronomy of the national academies, and I complained in frustration about my colleagues to members of the board, and one of them said, "Let me help you." It ended up in the White House. One of the people there reached out to the US Space Command. And in March 2022, the US Space Command issued a formal letter to NASA confirming at the 99.999% that they looked at the data and this object is interstellar. And they basically took time out of their day job, which is national security, to promote blue sky research. Department of Defense came to my defense. And I'm grateful for that. So our paper got accepted for publication. And the government also released data about the light curve of the fireball. And we used it to infer that the object was tougher than even iron meteorites, the toughest type of meteorites. And those are 5% of the meteorite population. So not only this is the first interstellar object, but it's actually not like the rocks that we are familiar with. So what was it? To find out, we went to the Pacific Ocean. And this is the light curve of the fireball. It showed 3 flares separated by 1/10 of a second from each other. At the low atmosphere of the Earth, where the stress exerted on the surface of the object was higher than on any other space rock, other space rocks would have disintegrated well above the place where this one did. It exploded about 10 miles over the Pacific Ocean. So the Department of Defense provided an error box that you can see here, and it was roughly 7 miles in size. That's a pretty large region. And we tried to narrow it down using data on the sound wave that was generated by the explosion. So just when you see, similarly to when you see a thunder, you hear the sound with a delay because the speed of sound is much slower than the speed of light. We were able to infer the distance of the explosion from a seismometer on Manus Island in Papua New Guinea based on the time delay, and we got a strip along with the meteor path must have moved. And that is shown in red within this DoD error box. So I organized an expedition a few months after I announced it. Of course, I didn't have the money. It's $1.5 million. A funder showed up on Zoom and said, "You have the money." I was happy. And then organized a team of 28 people, gladly the best in the world. Frankly, that was, again, a very fortunate situation, and I'm grateful for that. And you see them here on the deck of the ship. The trip was between June 14th and 28th this year, just a few months ago. And what you see behind the team is the so-called A-frame, which is a big structure through which we channeled the cable that was about 3 miles long, connected to the ship, and on the other end to a sled that we dragged on the ocean floor as we crisscrossed that region. We went 26 times back and forth to look for any molten droplets that fell off the surface of the object when it was exposed to the immense heat from the fireball that surrounded it as a result of its friction through air. So there was iron rain that came down on the ocean. If you were to hold an umbrella, it would puncture it. It's not a good place to be under. So here are some photos from that operation, and in the middle top image you can see the sled as we were pulling it out of the ocean, 1 mile deep. Just to remind you, this is a region of 7 miles in size. The ocean floor is 1 mile deep. we were looking for molten droplets the size of a grain of sand at the bottom of the ocean. Sounds hopeless, but if you don't search, you will never find anything. It's better to be an optimist in life, because life is often a self-fulfilling prophecy. If you tell yourself that you will not find anything, you will definitely not find anything. If you tell yourself you might find something, you might find something. So you can see us raising the sled from the ocean. What you see at the bottom left is the filming crew that was on the expedition. I had requests from 50 filmmakers and producers, 50, around the world that wanted to be on this ship, and I selected one. And every morning I would jog at sunrise, as I do on land. I jogged this morning at sunrise. One morning they decided to film me jogging as part of the documentary. And the director asked me, "Avi, it seems like you are running. Are you running away from something or towards something?" And I said, both. I'm running away from some of my colleagues who have very strong opinions without seeking evidence. And I'm running towards a higher intelligence in interstellar space. So here are some images of the sled in the top middle image, and the microscope that we used to look at whatever was on the sled after we scraped it. We used the vacuum cleaner to suck all the material from the magnets that were on the sled, as you see at the bottom images. So it was a lot of work, and actually I didn't sleep more than a few hours at a time, because we had 26 runs, many of them ending in the middle of the night. I slept on the couch in the conference room. And let me show you the work of the sled in one of the runs. So it looks like mowing the lawn, except it's on the ocean floor at a depth of 1 mile. There is life down there. We saw shrimp, we saw things moving around. And we were collecting magnetic particles. Most of them ended up being volcanic ash, black powder, that is of no interest to us. But we were looking for some molten droplets from this meteor, in addition to those. In the first day, the sled was not lying on the ocean floor because the cable was giving it a lift, so it was kiting above the ocean floor, but we ended up moving, the engineers found a solution to move with the ocean currents such that the sled will stay on the floor, and after the first day, we started collecting materials. Here you see a rock that was carried for the ride, but was not pulled up, of course. And we went 26 times back and forth across the region. We went also to control regions to see the background, so that we can distinguish what we find along the meteor path, which is shown in orange here. That's the expected meteor path. And altogether, we found 50 molten droplets, spherules they are called, on the ship. And I remember when the first one was found, I actually hugged the person who discovered the first one, because I knew that when you find an ant in the kitchen, there must be many more out there. And sure enough, we found 50 on the ship. And you can see here how they look. Very distinct from the sand around them, because they look like metallic marbles. And here are some photos of many spherules. My daughter, when she saw this, because I wrote 43 diary reports, and they were read by millions of people around the world and translated to Spanish, and so my daughter saw these images and she said, "Could I have one on a necklace? It looks beautiful." I said, "No way, these are millimeter in size, we can't thread them." And by the way, it's also a scientific expedition. So, and here are these babies that we delivered, the spherules, in the delivery room. So instead of babies lying in their beds, you see these spherules in vials. in a basket. Okay, and it was thrilling to collect 50 of them. But and here you see in one of the rainy nights, one of the runs, we were looking very carefully across the magnets to see if we found anything. The person to my right in this picture is the funder who also joined us, Charles Hoskinson. So then I brought the material back to Harvard. Actually, you can see the case, the black case that I used to ship the material with FedEx, because I was worried if I put it in my suitcase, it may get lost at customs. That's $1.5 million. You don't send it through customs. So I put it in a box, FedEx box, and shipped it. It took a few days for it to arrive to my home in Lexington. And I realized, well, a few days of a delay is not a big deal, because it took this material billions of years to arrive to Earth. So a few extra days of a delay is not too much. And then I brought it to a laboratory at Harvard that is managed by my colleague, Stein Jacobson, who is a very highly regarded geochemist. And he has the best, one of the best mass spectrometers in the world that you can see in front of us. He is the tall person standing here to my right. And on my left is a summer intern, Sophie Bergstrom, who came to Harvard. She wanted to shadow me because she had aspirations of becoming a science journalist. And at some point she said, well, maybe I can help with the science. And I said, great, we will be delighted to have you work on it. And so I arranged the tweezers and a microscope for her to look through the sample again. And in addition to the 50 spherules that we found on the ship, she found more than 600. So altogether we have over 700. I gave her the title, the Spheral Hunter, which she happily accepted. And here are some of the spherules that she found. And as we came back to the US through San Francisco Airport, we made a stop at the University of California at Berkeley and used the scanning electron microscope that they have to look at the inside of one of the spherules. And that's what we saw. We saw that inside those spheres, there are smaller spheres. It's just like Russian dolls. And you can see those smaller spheres are embedded in a matrix of dendritic material. They look like eggs. And the idea is that these small spheres solidified early because they were small, and then they were engulfed by liquid iron that glued them together. So it's quite beautiful to look inside of them. You can see lots of small ones. And as I arrived back to Harvard, I asked my postdoc Laura Domini to make a map of the yield of spherules, how many of them we found per unit mass retrieved, as we split the survey area into pixels. Each pixel is roughly half a mile in size. And what you see in purple are regions of relatively low yield, and in yellow, regions of high yield. So we went also far away, 10 miles away from the location of the meteor, and those are purple regions that you see on the left panel. And there is a zoom in of the central region near the meteor path, and you can see 3 yellow spots. These are the high-yield regions near the meteor path, and 3 of them may represent the 3 flares that came from this explosion. And amazingly, we found the spherules of a very unusual composition at those locations. We didn't find those unusual spherules anywhere else. And the fact that there is an enhancement in the yield of spherules along the meteor path is an indication that we visited the right place. So I sleep better at night, knowing that the US Space Command knows what they're talking about. Some of my colleagues, on the day that we came back, published a paper saying that the data must be wrong because they tried to fit the data with a model for stony meteorites. And they said, only if we lower the speed by a factor of 3, we get good agreement, and then it's a stone from the solar system, and therefore the data must be wrong. Now, that's a pretty arrogant statement to make, because the US Space Command gets funded with more money than NASA, and it's supposed to alert President Biden for any ballistic missile heading towards the US from North Korea, right? And if they were wrong by a factor of 3 in the speed measurement, they would alert Mexico for a missile heading towards Washington, D.C. That's unacceptable. How can astronomers make this point? So they made this point. And at the time that the point was made, I had in my hands those spherules that were made mostly of iron from the site. So apparently evidence is not enough in modern academia. It was not enough 4 centuries ago when the theologians refused to look through Galileo's telescope because they knew that the Earth is at the center of the universe. They didn't want to be confused by looking at data, at evidence. And I thought, by becoming a scientist, I can get to the bottom of questions, important questions, by looking at the evidence. But apparently I'm naive. That's not enough for some people. For me, it's enough. And so here are some images of those spherules. This is one that looks like a soccer ball. And here is another one that looks like a merger of 3 spheres that came together. And that one is pretty big, and it was in one of the yellow regions. So that was very interesting to us. It was the first that we analyzed, and we found a very unusual composition. So what you see in this plot is comparing various elements in the periodic table. That's the horizontal axis, starting from lithium on the left, going all the way to uranium on the right, and looking at the abundance of those elements relative to standard solar system materials. Okay, so the material that made the solar system came from a cloud of gas that was enriched by an exploding star nearby, and it shares the same abundance pattern throughout, at least initially. That was the case. And that's represented by 1 in the vertical axis, the solar system composition. But what we find is in red, as you can see, some elements being hundreds of times more abundant than solar system materials. These are elements like beryllium, lanthanum, uranium. Uranium is almost 1,000 times more abundant in this spherule than in solar system materials. We called it a Belau composition for beryllium, lanthanum, uranium. Stein Jacobson is a conservative geochemist. He came to me and said, I've never seen it before. This is not mentioned anywhere in the scientific literature. And we found it along the meteor path. So that's another indication that it came from interstellar space, the composition. And when we plot it as a function of the volatility of various elements, some elements can be lost during the explosion because of the immense heat. These are called volatile elements. We indeed see them missing. That's on the right side of this plot. They have abundances lower than solar system materials. These are elements that were lost, and that's an indication that this spherule came from an airburst. So then the question is, what was the origin, the source of this object? We could think of a planet that was a magma ocean. We discuss it in the paper. And if the planet has an iron core, some elements have affinity to iron, and they would sink to the center, to the iron core, and leave behind other elements in the crust of the planet, which we find to be more abundant in these spherules, the Belau spherules. So in principle, if there is a process that kicks out rocks from a planet that used to be a magma ocean, that could be a way of making them. But the composition is different than rocks on Earth, the Moon, Mars, or asteroids. So it must be a planet from outside the solar system. But it's also possible that these elements were selected for some technological purpose. We all know that uranium is used in fission reactors for energy production. Lanthanum, molybdenum are used as substrates for semiconductors. So who knows? We are planning a future expedition. But we definitely know, we looked at isotopes of iron, for example, we found that they have abundances very different from the solar systems. So very different from Earth, for sure, and so definitely not material that was on this Earth to start with. And so the best way to find out the origin is, of course, to find bigger pieces. And we are planning an expedition to do that. It's also possible, in principle, to go back to collections of meteorites and look for these fingerprints that we just identified in this case, and see if any other meteorites may have originated in interstellar space. And so we are currently planning, what you see here is an image taken at the end of the expedition after we had a champagne toast for the findings. And next to me is a very experienced navigator and the party chief on this expedition, Art Wright. And he didn't say much, but everything he said was right on target. And his expeditions were always successful, so I'm really grateful for his guidance. He was a commander on a destroyer during the Vietnam War. He's about 20 years older than I am, 25 years older. So I really enjoyed his company. We were looking at the sunset and thinking about the next expedition. And the goal is to find bigger pieces, because if you find a big piece, you can easily tell the difference between a rock and a technological gadget, because the gadget may have buttons on it. So in my last class at Harvard, I asked the students, if we find a gadget with buttons on it, should we press a button? So half of the class said, no way, don't do that. You know, you will affect all of us. And the other half said, please do, because we are curious to see what would happen. And then one of the students asked me, Professor Loeb, what would you actually do, given this split vote? And I said, I'll bring it to a laboratory and examine it before engaging with it. So don't worry. I'll be delighted to answer questions, and this is the cover of my book. If you want more details about the future implications of finding a technological gadget from interstellar space, you might find some interesting bits of information and projections for the future in the book. Thank you very much. Questions? Don't be shy. Yes, please.
Just wondering, on the future expedition, will it encompass some submersibles, dive teams, things like that? And also, are you getting any support, government support, now that you're showing promise in your work?
Well, during the expedition, I got some emails from the Pentagon, which were encouraging, so that was nice. By the way, I don't see any conflict between this scientific research and what the government is aiming at, because they are concerned with national security, and I don't care about any human-made objects, so we are complementary. And you know, they came to visit my home. A lot of people came to visit my home during the pandemic, and we are completely open, and you know, we are happy to help the government if needed. Indeed, the next expedition will use a different machinery than we used in the first one, because we want bigger objects. In the first one, we were looking for tiny millimeter-size droplets. So we could collect them with small magnets, but now we are looking for much bigger pieces. And to find them, well, we can't use divers. It's very deep. It's more than a mile deep. But we're thinking about various tools that we can use, maybe bigger magnets to distinguish them from basaltic rocks, for example, that may be on the ocean floor. We saw that in the video. We will have a video feed, which we didn't have in this case. The video that you saw was taken by cameras that were attached to the sled, but it was not in real time. We only were able to examine it after the sled was brought back to the ship. So now we want to connect the tool with a cable so that we can see in real time the ocean floor. And we will image the ocean floor and at the same time have the ability to collect big pieces. And we want to distinguish them from a lot of rocks that may be lying on the ocean floor. We might use an ROV. Actually, yesterday I had a conversation with someone that owns a boat that is much better than the one we used before that has an ROV with it. So we're still looking into the possibilities right now. The reason we just started planning for the next expedition is because just a couple of weeks ago we summarized the findings in a scientific paper. And we wanted first to see if the findings are interesting for us to do a follow-up. And so now we know that we want to do it. And I think it's a very exciting possibility. We are opening a new window into the universe. In the past, astronomers looked through telescopes to find what lies outside the solar system. We are using microscopes for that. Searching for interstellar meteors is a new frontier. Now, many of my colleagues would argue, first, you shouldn't have gone there because you wouldn't find anything. That's what they said before I went there. When I was there, they said, why are you writing essays about it? You haven't yet published a paper about your findings. And I said, because I don't feel superior relative to the public. I don't want to stand in front of the public and inform them of the final results without showing them how the process of scientific research is done. And people were inspired by that. So, and then when I came back, they said, you didn't find anything. And I said, what do you mean I didn't? Here is the paper. We found this composition. And they said, oh, well, how do you know that this composition does not exist somewhere in the solar system? And I said, well, tell me where, because we know what the moon has, the Earth, the Mars, and so forth. So some people just look for negativity, and the biggest damage that it does is in terms of young people watching it, because it discourages young people from innovating in science. When they see, I mean, if they want to have a job in academia, and they watch the response to any deviation from the beaten path, they get discouraged. And of course, that's the purpose of those senior people who are, pushing back. And I see that as a very alarming facet of academia now. Not only that most people do not take any risks, despite the fact that they have tenure, and that was designed for the purpose of maintaining job security while voicing opinions that are not yet accepted. But not only that they're not engaged in that because they're chasing honors, awards, and dancing to the tunes of selection committees, which is basically what drives them. But moreover, when someone else does it, they push back in a way that is not professional. And that I have complaints about. At any event, I'm not just making my case by writing books and scientific papers. I'm actually doing the scientific work as well. So hopefully, once we have good enough evidence, we can bring clarity to whether any of the interstellar objects might have a technological origin. And obviously, that would be the most important discovery that science ever made, because it will change our aspirations for space. It will allow us to be inspired by technologies of the future, which was the past of other civilizations, and also change our priorities to work together rather than fight with each other, which you already see from the hearings in the House of Representatives that brought the two parties together when they dealt with this subject. Thank you.
Thank thank you, Dr. Loeb, for such an enjoyable talk, and thank you to everyone for joining us today. We hope you'll be back here for our next event on October 25th, when we'll be joined by author Daniel Gagnon. If you're interested in purchasing your own copy of Extraterrestrial or Interstellar, you can go in the back table, and someone will help you out. Thank you again to Dr. Loeb for today.
Yeah, and I'll be down there to sign books if any of you wants to have them.